All right, hi folks, this is Larry Mussolino. I wanted to record a short video here for Module 3. This is the Chapter 5 homework. And Chapter 5 really deals with a lot of probability type calculations. So let's get started. I want to come here to number 2. This is more of a conceptual question. It says, in many state lotteries, you get to choose which number to play. Common lottery is where you get to pick 5 numbers. Which of the following strategies can improve your chance of winning? What if you decide to always play the numbers 1, 2, 3, 4, 5? Will that improve your chance of winning? Well, if you think about it, picking any 5 numbers, it's really not going to matter which numbers you pick because every group of 5 numbers is equally likely to be selected in a lottery. Right, we're assuming here that when they go to pick these lottery numbers, every number has an equally likely chance to be selected. So if you pick 1, 2, 3, 4, 5, that's equally likely than picking, 5 random numbers like 10, 17, 23, 29, 31. I pick 2, 4, 6, 8, 10. It doesn't matter. Every group of 5 numbers has an equally likely chance to be selected. So is this going to improve your chance of winning? No. Each number drawn is equally likely. So this set of numbers is just as likely as any other. So if I pick 1, 2, 3, 4, 5, that's exactly the same probability of winning as if I picked 5 random numbers. Part B says, what if you pick random numbers using a computer? Will that improve your chances of winning? Well, the same argument. No, because each number is equally likely. So random numbers are just as likely as any other group of numbers. All right, let's do another example. Let's come here to number 4. All right, so this one says you and your friend decide to get your cars inspected. You know that 81% of cars pass inspection. Let's assume your car's passing is independent of your friend's car. That means it doesn't really matter what happens with your friend's car. Your car is either going to pass or not pass on its own merit, right? What happens with your friend's car has no influence or no impact on whether your car is going to pass inspection. So they're like totally separate and totally independent events. All right, let's go to part A. What's the probability that your car passes inspection? Well, every car has an 81% chance of passing, so my car is going to have an 81% chance. What's the probability your car doesn't pass inspection? Well, there's a probability rule. By the way, we would say the probability of event A is 0.81 for part A. Event A would be your car passing inspection. Well, here we want to know what's the probability that your car doesn't pass inspection. Well, the probability that the car doesn't pass inspection is equal to 1 minus the probability it does pass inspection. Sometimes we call this the complement. Well, we know the probability the car passes inspection, that's 0.81. 1 minus 0.81 is 0.19. That's kind of like saying there's an 81% chance your car passes. Well, by the same token, you could say the remaining percentage, 19%, is the chance it's going to fail inspection. All right, what about the probability that both cars pass inspection? Well, there's a probability rule. If you want to know the probability that your car passes and your friend's car passes, if the two events are independent, you can write that as P of A times P of B. So I'm just going to multiply the probabilities together. Well, the probability that my car passes is 0.81. The probability my friend's car passes is also 0.81. So if I multiply 0.81 times 0.81, I get the answer 0.6561. All right, that was part C. Let's go to part D. Part D is a little tricky. It says, what's the probability that at least one car passes inspection? Well, if I want to know the probability of at least one, the formula to use here is it's going to be 1 minus the probability that none of them pass inspection. Right? Because if you think about the probability that no car passes inspection, the complement of that is at least 1. So this is a probability formula that's very handy. If you want to know the probability of at least 1, it's 1 minus the probability of none. Well, the probability of none would mean that it's the probability that my car fails and my friend fails inspection, right? Because if we both fail, that means none of us passed. Well, the probability that I failed, my car fails, is 0.19. We worked that out here in part B, so this is 0.19. But the probability that my friend car fails is also 0.19. Friend car fails. Well, it's also 0.19. So this is going to be 1 minus 0.19 times 0.1. If you work this on your calculator, you get 0.9639. So whenever you see a question that says, what's the probability of at least one? Think of it as 1 minus the probability of none. All right, let's take a look at another example. Let's go to number 5 here, maybe. All right. So the next couple of examples are going to give you these tables and ask you to come up with probabilities based on analyzing a table like this. All right, so let's look at the table first. It looks like political party are the rows, and the columns are the opinions on global warming. All right, well, let's take a look at the first question. It says, what's the probability that a registered voter thinks that global warming is a serious issue? So I want to know the probability that people think global warming is a serious issue. Well, whenever you want to find a probability like this, you set up a fraction. The top of the fraction is the number of people that think it's a serious issue divided by the total number of people we asked. Well, for our example, the number of people that think it's a serious issue is this column right here. All of these people think global warming is a serious issue. Well, they added up this column for us at 750. So a total of 750 people think global warming is serious. How many people did we ask in total? Well, this whole table represents 1,200 people. So I'm going to work out 750 divided by 1,200. That works out to be 0.625. Now, if you notice, we really calculated a probability based on this column. When you calculate a probability based on a column or a row, we call that a marginal probability. Marginal really refers to either a row or a column. All right, let's go down to the bottom example then. The bottom example says, what's the probability that a voter is Republican and thinks global warming is serious? Well, this row are all the people that are Republican. But I don't want all the people. I just want the people that think global warming is serious. Well, that means I have to go to the intersection of this row and column, which means the number 200. So for this probability, I'm going to set it up to be the number 200 divided by 1,200. Because I needed the number of people that were both Republicans and think global warming is serious. Well, that number is 200 from the table. And if I work this out on my calculator, I get 0.167. Well, notice we were figuring out a probability for the intersection of a row and a column. For that, we call that a joint probability. All right. Let's do another example here. All right, let's take a look at this one. So it says here, multi-generational families are having two adult generations, such as parents living with adult children. Skip generations are where grandparents live with grandchildren. And you might have three or more generations living in a household. All right, so let's take a look at this table. All right, so it looks like they collected data for either two adult generations, two skip generations, or three or more generations, and they did it by different races: white, Hispanic, Black, Asian. All right, let's take a look at the first question. It says here, what is the probability that a randomly selected Black multi-generation family is two adult generations? And notice this is really asking me to focus just on the row for the race of Black. So they're really asking me to just focus on this row for this question. And they want to know, what's the probability that it's a two-generation family? Well, for this probability, the number we want is 117. But they only wanted us to focus on Black families here. That means I should just use the total of 250. So 117 over 250 turns out to be 0.486. Sorry, 0.468. All right, let me go to part B. It's a little tricky using this table for some of these questions, so you really got to read these problems carefully to understand what they're asking us. Go to part B. What's the probability that a randomly selected multi-generational family is white, given that it's a skip generation family? Now, when you see the word given, the word given is telling you, let me write it here. If you see the word given, what it's telling you is focus only on the row or column that's being specified in the given statement. So notice they said skip generation family is what we're interested in. Well, that means restrict yourself to only this column. We're only going to be looking at this column. And they want to know, what's the probability that a family is white? Well, here are the white families, 58. So the answer to part B is going to be 58 over the column total of 99. And if you work this out on your calculator, you get 0.586. So the reason I only focused on this column of two skip generations is that was the given statement that I was provided. What that meant is ignore these other columns. I'm only going to use the two skip generation column to answer this question. And they wanted to know, what's the probability of white? So I took 58 divided by the sum of that column, which is 99. All right, let's go to part C. Now, sometimes they use a vertical bar to mean given. So when you see a vertical bar right here, can you see this vertical bar right here? A vertical bar means given. So what they're asking me here is, what is the probability that there's three or more generations given that it's an Asian race? Well, if they say given Asian, focus only on that row or column. So I'm going to focus only on this row. Ignore the rest of the table. I'm going to cross out the rest of the table because I'm not going to look at the rest of the table. I'm only going to look at the row for Asians. And they want to know, what's the probability of three or more generations? Well, three or more generations is this number 43. And I'm going to divide it by the row total of 110. And 43 divided by 110 is 0.391. So again, the key to this kind of analysis is whenever you're given some, given skip generation, given Asian. That's really telling you to focus only on that row or column that's specified in the given statement. Cross out any other rows or columns in the table. All right, let's do a few more here. Let's go maybe to number 8, let's say. All right, this is conceptual, just asking us to interpret some statements. Let's go to part A. A casino claims its roulette wheel is random. What does that mean? Well, if it's a random roulette wheel, it means that the ball, if you know the game of roulette, the ball is equally likely to fall in any one of the 38 slots on the roulette wheel. That means the outcomes are equally likely and they're independent. Independent means what happened on the previous spin has no effect on the next spin. Each spin is like its own separate outcome. There's no dependence. There's no memory to the roulette. Let's go to part B. A stock market reporter says there's a 50% chance stock market's going to hit a new high. What does that mean? Well, that's really that person's personal probability. That's what they think, right? There's no certainty or guarantee of that. It's just their impression or their subjective probability. All right, let's look at one more maybe. All right, let's look at, let's put another one here. Yeah, let's take a look at this one. This one says, for a sales promotion, a manufacturer puts winning symbols under the caps of 29% of its soda bottles. Let's say you buy a 6-pack of soda. What's the probability that you win something? Well, really what this is asking you is you might win based on one bottle out of the 6-pack. You might win based on 2 bottles, right? 2 caps might be winners, or 3 caps, or maybe all 6 caps are winners. That's pretty unlikely, but it's possible. So what's the probability that you win something? Really, it's asking you, what's the probability of at least one winning cap, right? That's really what they're asking us here. Well, if you remember from previous example, the probability of at least one winning cap is 1 minus the probability of no winning caps. Well, what's the probability that you don't win for one of these bottles? Well, the probability of winning on a soda bottle is 0.29. So the probability of not winning is 1 minus 0.29, which is 0.71. But for me to not win, it means I didn't win for soda bottle 1, so no win for bottle number 1. And there was no win on bottle number 2. And there was no win on bottle number 3, and so on. Well, really, when you have the word and, it means multiply the probabilities together. This is going to be 0.71 times 0.71 times 0.71, etc. This is going to be 6 of them. ... So my answer here is really going to be 1 minus 0.71 to the exponent 6. Because the probability of no winning caps is going to be 0.71 times itself 6 times. And if you work this out on your calculator, you'll get 0.872. So that's a pretty high probability that you're going to win something on this 6-pack of soda. All right, folks, hope this is helpful as you're working in Chapter 5. I'll record a separate video for Chapter 6 with a few worked out examples as well.